Innovalia Metrology is an alliance of high-tech SMEs, aiming to provide a holistic solution for dimensional quality control, with an international presence in strategic sectors like automotive, aeronautic, renewable energy or railways. M3 Zero Defect Manufacturing connects metrology with the digital thread of your products, bringing total quality control through their life cycle. But experts still need to visit factories physically to configure machines and design processes, meaning slower, less flexible manufacturing. And while COVID-19 has just proven how much this is a bottleneck, it has shown the full potential of remote working. In this context, and within the 5 Growth European project, Innovalia is teaming up with technology giants such as Telefonica, Ericsson, and more, to create the 5G-based, people-centric, metrological services of the future. This innovation is developed in first-class facilities like the Automotive Intelligence Center, in Bilbao, and the 5Tonic Labs, in Madrid. Industry and Metrology 4.0 are evolving into fast, accurate, reliable, flexible, and holistic processes. Digitization and 5G cannot be seen as mere enhancements, but rather as essential tools for the transformation of the quality control paradigm. Thus, 5 Growth architecture and technology are vital enablers for more autonomous human-machine information interactions. The purpose of this use case is, first, to validate the capability of 5G technology to enable remote operation of industrial machinery, by providing a secure communication, delivering high data rate and keeping a low end-to-end latency between devices. And second, to reveal the maximum distance between devices that keeps granting a smooth remote operation. This is the description of the use case. A metrology expert, located at Innovalia headquarters, interacts with the M3 metrological software, in order to control a coordinate measuring machine, or CMM, installed at the manufacturing site, and equipped with an optical scanner. Besides, a camera is installed in order to stream, in real life, the movement and positioning of the CMM relative to the part to be measured, allowing the expert to have all the information required for the proper operation of the quality control device. All the communications between the expert and the CMM, including commands, metrological results and video stream, are done through 5G connection in the 5 Growth platform. 5G provides a reliable high-throughput performance, with a consistently low latency, improving previous mobile generations. This is vital for this use case, since it leaves higher margin to operate the machines from far distances. And this, coupled with the increased flexibility, automation and simplicity associated with the innovations developed under the 5 Growth project in terms of orchestration and layer instantiation, are key enablers to unlock novel capabilities and business models, even for SMEs, that were until now blocked by technical constraints. Specifically, Innovalia Pilot aims at obtaining 5G connected quality control services for Workers 4.0, connecting anywhere, anytime, the M3 metrology software with the coordinate measurement machine and video system. This enables personalized, remote decision and quality control assistance. The idea is to be able to control the configuration of the quality process without the need to travel on site, even with sites located at medium to far distances, for example, trips along Spain. Additionally, the vertical application is deployed on the network edge of the 5G architecture, and only when needed. This saves costs for the vertical, as they do not need to maintain the hardware and the application at all their customers' premises. The deployment would be extremely beneficial not only in terms of reduced expenses in travels, but also in terms of reduction of the response time, increase in the productivity of the metrological expert, and reduction of the carbon footprint related to business travel. Overall, industries will benefit from the ubiquity of 5G commercial networks connectivity, that will allow to instantly connect devices anywhere, in a faster, cheaper and more flexible way than cable. We have run this use case at 5Tonic with the following setup. On the one hand we have the M3 software and the display, and on the other hand the CMM, the virtual application and the camera. Those devices are connected to the 5G network installed at 5Tonic Lab via CPE routers. We have also configured the IP addressing, achieving connectivity between end devices. Probes have been developed to measure the metrics. In this experiment we deployed one probe on the entry router to the 5G evolved packet core, and a second one on the Raspberry Pi camera. Available ready resources are important for the achievable performance. We are using the 3.5 GHz band. The available bandwidth is 50 MHz. The TDD pattern is 7:3. We are using 256 QAM modulation and a 4x4 MIMO. Under these conditions we have measured in the RAN a peak data rate of up to 544 megabits per second in the radio downlink, and a peak data rate of up to 54 megabits per second in the radio uplink. As device-to-device traffic in this use case includes a radio uplink segment, that is the top data rate that can be achieved. When measuring latency in this use case, the following considerations must be taken into account. The traffic travels through different segments and components. There are network-related latencies that will impact all kind of traffic. The one-way delay values introduced will be up to 10 milliseconds on a first RAN segment, half a millisecond per 100 km on the transport segment, close to 0 between the edge and the RAN, and up to 10 milliseconds on a second RAN segment. Also, there are application-level latencies that will have a different impact on the overall latency depending on the application. For example, for the command traffic, there will be a latency of 5 milliseconds on the edge caused by the processing of the commands. For the video streaming, there would be a latency of 50 milliseconds of the video encoding on the camera. No delay on the edge, as there is no processing there in this case. And finally, a latency of 25 milliseconds of the video processing for visualization. This is the actual look of the setup at 5Tonic Lab. On the big central picture, we can see the user and devices involved in the use case. The devices on the left of the image belong to the remote control area and are connected to CPE1. The scanning area is on the right of the image. On the top pictures we can see the 5G antennas that provide coverage at 5Tonic Lab. On the bottom right picture, we can see the backpack that is holding the 5G RAN and 5G Evolve packet core equipment. In order to deploy the service, 5Growth and 5G Eve platforms are integrated. The VNF packages, blueprints and descriptors are onboarded on the platforms. And the instantiation and termination operations are triggered in the 5Growth vertical slicer. Next, we are going to see how to instantiate Innovalia service.
Log into the vertical slicer. The Innovalia blueprints and descriptors are onboarded and ready to be used. Go into the vertical service instances section. Fill in the details. Select the available descriptors. Specify the blueprints and submit. This action triggers the instantiation, and eventually the network service request reaches the service orchestrator. After all deployment and configuration activities are completed, the vertical service will be instantiated.
This is a video recorded while experimenting with the use case. On the scanning area, the machine is operating. The process is being captured by the camera on the right. We have placed a panel in the middle, to block the line of sight. From the control area, the technician is controlling the CMM. He can move the machine, and while the machine moves, the piece gets scanned and the metrology results are sent to the M3 software. We can see that the video quality is good enough for the technician to control the machine, and that the M3 projects the results aligned with the movement of the coordinate measuring machine. While running the use case, these are the metrics that have been observed. On the upper part of the slide, we found the metrics of the video streaming traffic, measured by the probe on the Raspberry Pi camera. Note that the latency measured is the round-trip time since the packets leave the Raspberry Pi towards the display on the other end until the ACK is received back. This value is around 45 milliseconds. The data rate demand is constant and is 20 megabits per second. The lower part of the slide is showing the metrics for traffic between the CMM and the M3 software. These flows are measured by the probe on the router. The yellow line shows that communications sent towards the CMM have a round-trip time of 15 milliseconds between the core and the CMM, and a data rate demand of under 1 megabit per second. The green line shows that the optical scan results sent towards the M3 software have a round-trip time of around 15 milliseconds between the core and the M3 software when there is traffic, and a data rate demand of up to 7 megabits per second. To study the effect of the distance between locations, we have correlated the KPIs and the distance. We have added a VM in the path, where we use the network emulator tool to shape the traffic delay. We have obtained the KPIs for different distances. At 0 kilometers, the experience was scored as good by the Innovalia expert, and we measured, as we said earlier, an RTT latency of 45 milliseconds. Later, for a distance of 2,000 kilometers and 3,000 kilometers, the experience was scored as acceptable. Finally, for a distance of 4,000 kilometers, the experience was perceived as bad. Thus, the maximum radius of operation would be around 3,000 kilometers. This map represents the results in a concrete manner, with a radius of 3,000 kilometers centered around the Innovalia headquarters, located in Bilbao. As we can observe, this means that the theoretical distance that this solution enables to cover is wide, enabling to fully operate factories all over Europe. This result is in line with the business requirement from Innovalia, and presents a huge improvement, only possible due to 5G technology innovations. Let us see in deeper detail the results obtained for 3,000 kilometers. This is the graph of the distribution of the measurements of RTT-TCP latency. The average is 75 milliseconds. Just 30 milliseconds over the reference value. As expected. The 90% of the measurements are between 65 milliseconds and 86 milliseconds. And the 99% of the measurements are between 64 milliseconds and 94